In this section, we're going to examine thermal stresses in a laminate. And just as we've done with in-plane loading and bending so far, we're going to restrict ourselves to a symmetric laminate. We'll go on in section 7 to look at general laminates, that is, ones that aren't symmetric, but we find that the most useful laminate designs tend to be symmetric, and so we'll restrict ourselves to that for the moment. So why are thermal stresses so important when we look at composite materials? Well, basically it's because you're going to have a laminate, and it's going to have different layers in there, and almost certainly it's going to have layers of different orientations, might even have different materials in there. But even if it's just the same material, but the angles are different, you're going to have different thermal coefficients. And what that means is when you go up to the cure temperature, if it's going to be an elevated temperature cure, the resin can flow until you get up to that cure temperature. Then once the cross-linking of the resin begins, you've really locked in the orientation at that point, so we call that the stress-free temperature. And when you come back down to room temperature, then you're going to have some stresses that get built in, and those residual stresses can actually be kind of high. Also, if you don't have a symmetric laminate and you do this curing, if you go in with a flat laminate, put it in the oven, and it's not symmetric, when it comes out of the oven, it's going to be bent. So let's talk about free thermal strain for just a moment. So here's a composite layer, it's just an arbitrary orientation for now. And if we don't have any constraint on the laminate, you know that just like with a isotropic material, if we take an aluminum bar and heat it up and we don't constrain it at all, we're not putting any stress on it, but it will grow in in all directions. Now in this case, we're saying that certainly with a fiber reinforced layer, that the thermal coefficients in the fiber direction and transverse to the fiber are going to be different. And so we get these free thermal strains. The superscript T just means free thermal strains of the thermal coefficient times delta T in the fiber direction and in the transverse direction. And again, in the if we're totally unconstrained, it's not going to warp or shear one way or the other. So gamma 1, 2 would be equal to 0 here. But we need to transform those into global coordinates. And so as with any strains, we can use the T2 inverse matrix to transfer those. And so what we have on the right, those new free thermal strains would be related to our thermal coefficients alpha x, alpha y, and alpha xy in global coordinates. Each of those times delta t would give us the free thermal strains in the global coordinates. And so once again, there's the T2 inverse matrix, and so we can kind of write those out in this form: alpha x, alpha y, and alpha xy. And I would put it in that form because that'll be easier for you if you want to put that in those into your spreadsheets to be able to calculate the thermal coefficients in the global coordinate system. All right, now important to remember that as we said, free thermal strains are not associated with stresses. So your stress-strain relations really apply to mechanical strains. And so your total strain is going to have the mechanical strain and the free thermal strain together, which means that your mechanical strains, again the ones that we're interested in that are associated with stresses, we have to take the total strains and subtract off those free thermal strains. So we can write it as shown on the bottom line here once we put in the stress-strain relations, that the stresses are equal to the Q-bar matrix times the strains, and again, just the mechanical strains, so the total strains minus the free thermal strains. So we can do that in local coordinates as well. We can have the stresses in the local coordinate system be equal to the Q matrix times the mechanical strains, but once again, take the total strains in the layer and subtract off the free thermal strains. And again, since there is no alpha 1, 2, then that becomes 0, so you don't subtract anything off of the shear strain gamma 1, 2. All right, so remember our definition of the stress resultants. If we take the stresses in each layer, multiply them by the thickness, and sum those up, those are the stress resultants, in-plane stress resultants. And so we can put in our definition for strain that we came up with for the last time for each layer and rearrange that a little bit. So you can see what I've got is the A matrix times the total strains minus that summation, which includes for each layer the Q bar, the thickness, and the alpha values of that layer, all times delta thickness. Excuse me, delta temperature, sorry. And so what's on the right side there after the minus sign, those are the thermal stress resultants. Ins of xt, ins of yt, ins of xyt. And so we can write those out like this. If we take the first row of the Q bar matrix, multiply by the thermal coefficients, multiply that by the thickness for all the layers, sum those up for all the layers, multiply by delta t, then we have ins of xt. Similarly for ins of yt and for ins of xyt. The only difference is now we're using for ins of yt using the second row of the Q bar matrix, and for ins of xy we're using the bottom row of the Q bar matrix. So those are the thermal stress results. So if we move those back over to the other side of the equal sign, we can say, okay, once we calculate those thermal stress resultants, we can add those to any other applied load that we have and set that equal to the A matrix times the total strains. And again, doing the inverse of that, again, we have mechanical loading, we have temperature change, we add all that together, multiply by the A inverse matrix, and we get the total strains, epsilon x, epsilon y, and gamma xy. And from that, we could say if we have thermal loading only, then we can calculate the laminate's thermal coefficients by taking the strains, again, just due to thermal loading, and for each one of those dividing by delta t. I've used a bar over the alpha x, alpha y, and alpha xy to show that they apply to the entire laminate instead of an individual layer. So we can also write that out as shown here. The alpha coefficients, the laminate thermal coefficients, based on the A1 inverse matrix and the thermal loadings. I know that's kind of a lot to go through here, but it'll make a lot more sense when we look at an example here. So we have all of the details, all of the calculations set up and ready to go, and in the next video we'll do an example.